This helicopter broke speed barriers that helicopters weren't supposed to break, and its strange design is the reason why. At first glance, it looks wrong. Almost like someone took a normal helicopter, attached airplane parts to it, and hoped for the best. But every weird shape, every unusual component, and every design choice exists for one incredible reason. And by the end of this story, you'll understand why some engineers believe this machine changed the future of vertical flight forever. For decades, helicopters had a problem nobody seemed able to solve. No matter how powerful the engine became or how advanced the technology got, there was always a wall waiting ahead, a speed limit. Push too hard toward it, and the laws of physics started pushing back. The problem came from the rotor itself. The very thing that allowed a helicopter to hover was also the thing preventing it from flying much faster. As speed increased, one side of the rotor moved through the air faster, while the other side slowed down. Eventually, the slower side couldn't generate enough lift. Engineers called this retreating blade stall, and once it happened, things could get dangerous very quickly. Now imagine being an engineer staring at that problem. Generations of designers had tried improving helicopters, yet the same barrier remained. Faster engines didn't solve it. Better materials didn't solve it. Even advanced rotor designs struggled against the same invisible enemy. For many people inside the aerospace industry, the conclusion seemed obvious. Helicopters had reached their practical speed limit. But Airbus Helicopters wasn't satisfied with that answer. Instead of asking how to build a faster helicopter, they started asking a completely different question. What if they stopped thinking like helicopter designers altogether? What if the solution wasn't hidden inside the rotor system? And this is where things get interesting. Because the team wasn't planning to improve the helicopter. They were preparing to reinvent it. How do you make a helicopter fly dramatically faster without sacrificing the ability to hover? Nobody knew yet. But Airbus was about to test an idea that looked completely insane on paper. To answer that question, Airbus engineers started building something that looked unlike any helicopter before it.
You know, when you fly, you don't really notice the speed. My name is Hervé Jamerac, so I'm a test pilot, experimental test pilot at the Eurocopter.
The first time people saw the Airbus X3, many had the same reaction. What exactly is that? It had a helicopter rotor on top. That part made sense. But then there were these short wings sticking out from both sides. At the end of those wings sat giant propellers. And suddenly it looked less like a helicopter and more like some kind of aviation experiment. But here's the thing. None of those strange features were there for appearance. Every single one had a job to do. The foundation of the aircraft came from the proven AS365 Dauphin helicopter. Airbus started with a platform they already trusted. Then they began adding components that completely changed how the aircraft would behave in flight. The most obvious additions were the short stub wings. Helicopters normally don't need wings. So why add them? Because Airbus wanted something extraordinary to happen once the aircraft accelerated. Then there were the side-mounted propellers. Unlike a traditional helicopter that relies heavily on its main rotor for forward movement, these propellers would eventually become one of the most important parts of the entire design. Even the tail looked different. Conventional helicopters use a tail rotor mainly to counteract torque from the main rotor. The X3 approached that challenge differently, allowing engineers to rethink the aircraft's overall layout. And little by little, the strange-looking machine started making sense. What seemed weird was actually intentional. What seemed complicated was actually clever. The weird appearance wasn't a compromise. It was actually the secret weapon. But there was still one massive problem. Designing something unusual is easy. Making it work is another story entirely. Could these wings and propellers really solve a problem that had limited helicopters for generations? Or was Airbus chasing a dream that physics would eventually destroy? To find out, Airbus had to engineer one of the most complex power systems ever installed in a rotorcraft. Making the X3 happen wasn't as easy as just slapping propellers onto a helicopter and crossing fingers. It was more like getting almost every big system to agree at the same time. One hiccup, one small failure somewhere, and the whole idea could quietly unravel. The airframe, for its part, needed more than a simple tune-up. The engineers reinforced the frame and brought in advanced composite materials, able to take severe loads that regular helicopters rarely see, at least not for long. Fast flight was going to throw huge strain into the airframe, and Airbus also understood there was zero tolerance for anything even slightly flimsy. In the middle of the machine sat a sharp and complex rotor setup. A titanium swash plate handled the blade pitch with almost unreal precision. Meanwhile, the 5-blade main rotor leaned on helicopter experience that had already been validated on the EC-155. Airbus wasn't leaving that behind. They were, in a sense, extending it. And then you reach the heart part. 2 powerful RTM322 turboshaft engines were fitted above the fuselage. Those engines did more than just spin up the main rotor. Their power also had to carry through to the large propellers placed at the ends of the wings, so everything would keep pulling its weight. That required an incredibly complex transmission setup. A massive gearbox became the aircraft's central hub. Power flowed through drive shafts, extending into both wings before reaching secondary gearboxes near the propellers. It was a mechanical balancing act unlike anything found in traditional helicopters. And then there were the countless supporting systems: hydraulic controls, digital monitoring equipment, engine management software, vibration sensors, cooling systems. Every component had a role in keeping the aircraft stable at speeds helicopters weren't supposed to reach. Slowly, the machine took shape. Rotor blades were mounted, propellers were installed, control systems came alive. For the first time, engineers could step back and see the complete aircraft standing inside the hangar. It looked futuristic. It looked strange. And honestly, it looked risky. Everything looked impressive on paper, but none of it mattered unless the aircraft could actually fly. Would this complicated machine perform as intended once it left the ground? In September 2010, the moment of truth finally arrived. Years of design work, thousands of engineering decisions, countless hours of testing. Everything had been leading to this moment. On September 6, 2010, the Airbus X3 prepared for its maiden flight. Engineers watched closely. Test pilots climbed aboard, and suddenly the project stopped being a theory. Now it had to prove itself. The engines came alive first. Then the rotor began turning overhead. Slowly at first. Then faster. For a few tense moments, nobody knew exactly what would happen next. And then the aircraft lifted off the ground. The hover was stable. That alone was a huge relief. Despite its unusual appearance, the X3 behaved like a helicopter when it mattered most. It could rise vertically, hold position, and perform the basic tasks expected from any rotorcraft. But Airbus hadn't built the X3 to be ordinary. The real test came when pilots began exploring the aircraft's unique systems. The side propellers were gradually introduced into the flight profile. As they generated forward thrust, the aircraft started behaving differently from conventional helicopters. Engineers closely monitored every response, every vibration, every movement. What they saw was encouraging. The aircraft remained controlled, stable, predictable. And with every successful flight, confidence began to grow. The X3 wasn't just surviving. It was performing exactly as intended. But this was only the beginning. Flying was one thing. Flying faster than almost every helicopter ever built was something else entirely. The aircraft flew, but the real test was still ahead. How fast could this strange machine actually go before physics fought back? The engineers now had enough confidence to start pushing the aircraft toward territory no helicopter was supposed to reach.
Flying at 255 knots, which is like 100 knots faster than the conventional helicopter. We broke the record. The sensation of I would say, opening the envelope and pushing the envelope. And this is the job of the test pilot, pushing the envelope. But we know that with the X-Cube, we've pushed it quite far.
And this is where everything changed. The X3's greatest breakthrough wasn't a powerful engine or a revolutionary rotor. It was something much smarter than that. As the aircraft accelerated, the small wings that looked so unusual suddenly became incredibly important. Instead of forcing the main rotor to carry all the lift, the wings began taking over part of the workload. The faster the X3 flew, the more lift the wings generated. In some flight conditions, those wings carried between 40 and 80% of the aircraft's lift. That changed everything, because now the main rotor didn't have to work nearly as hard. Engineers could actually reduce rotor speed by roughly 15% during high-speed flight. That might sound small, but it helped tackle one of the biggest problems in helicopter aviation. The retreating blade stall issue that had haunted designers for decades suddenly became far less severe. At the same time, the side propellers pushed the aircraft forward. Instead of relying primarily on rotor tilt for speed, the X3 had dedicated propulsion systems generating thrust. The result was remarkable. The rotor focused more on lift. The wings helped support the aircraft. The propellers delivered speed. 3 different systems working together as one. And somehow, despite all these changes, the X3 never lost its helicopter DNA. It could still hover. It could still take off vertically. It could still perform the tasks expected from a rotorcraft. That combination was what made the design so powerful. Airbus had found a way around a barrier many thought was permanent. Now that Airbus had solved the speed problem, there was only one thing left to do: push the aircraft harder than ever before. Because solving the problem in theory was impressive. Proving it with record-breaking speed would be something else entirely. How close could the X3 get to the impossible speed targets engineers had dreamed about? The answer would emerge during a series of increasingly aggressive test flights. Now came the part everyone had been waiting for. The engineers knew the concept worked. The pilots trusted the aircraft, but nobody knew where the limit actually was. So Airbus started pushing harder. In May 2011, the X3 blasted past 232 knots. What's crazy is that it achieved this while using less than 80% of its available power. That got everyone's attention. Suddenly, the team realized they weren't close to the edge yet. And then, the speed program became even more aggressive. Flight after flight, the numbers kept climbing. By June 2013, the X3 entered aviation history. It reached 255 knots in level flight and 263 knots during a shallow dive, translating to roughly 472 kilometers per hour. In doing so, it surpassed the famous Sikorsky X2 benchmarks that many thought would stand for years. Breaking speed records was impressive, But what shocked pilots even more was how the aircraft behaved at those speeds. Did extreme speed come with dangerous instability? Surprisingly, the answer was exactly the opposite. You'd expect an experimental aircraft flying at record-breaking speeds to be nervous, unpredictable, maybe even uncomfortable. But that's not what the pilots reported. Instead, test crews described something unexpected: stability. Even at speeds where conventional helicopters begin struggling, the X3 remained remarkably smooth. Pilot reports highlighted minimal vibration, despite the aircraft not using active anti-vibration systems. That alone surprised many experts. And the performance didn't stop there. The X3 could climb at around 5,500 feet per minute and perform sustained 2 G-turns at speeds that would challenge traditional helicopters. It could bank aggressively, accelerate rapidly, and still maintain the hover flexibility that makes helicopters so useful in the first place. This wasn't just a speed machine. It was becoming something much more interesting. The X3 wasn't just fast, it was proving to be practical. If it worked this well, what could it actually be used for in the real world? Airbus believed the technology could transform multiple industries. At this point, Airbus had already proven the X3 was fast. Really fast. But speed alone wasn't enough. Nobody spends years building an aircraft just to break a record and call it a day. The bigger question was what this thing could actually do in the real world. And that's where the conversation started changing. Imagine you're stranded on an offshore oil platform hundreds of kilometers from shore. Or you're waiting for a rescue helicopter in rough weather. In situations like that, every minute matters. Airbus believed the X3 could cut those travel times dramatically. The more people looked at the aircraft, the more possibilities appeared. Search and rescue missions, medical evacuations, Coast Guard operations, even passenger transport. It could take off like a helicopter, land where airplanes couldn't, and still travel at speeds that seemed almost unfair. And for a while, it felt like Airbus might be looking at the future of rotorcraft. But here's the thing. Sometimes an aircraft's biggest achievement isn't what it does in service. It's what it inspires next. Would the X3 actually become the machine that changed aviation? The answer wouldn't become clear until its flying days were over. By 2014, the X3's job was finished. Not because it had failed, because it had succeeded. After more than 140 flight hours, engineers had gathered the data they needed. The aircraft had proven its point. The strange-looking helicopter that many people doubted in the beginning had shown that the old speed limits weren't as permanent as everyone thought. Then came a moment that felt strangely emotional. The X3 was retired and moved to a museum in France. No more record attempts. No more test flights. No more chasing impossible numbers. For most aircraft, that's where the story ends. But not this one. Because while the helicopter stopped flying, the ideas behind it kept moving forward. Engineers took what they learned from the X3 and began applying it to future high-speed rotorcraft programs. The project became a stepping stone toward aircraft that could one day travel farther and faster than traditional helicopters ever could. And when you look back at it now, that's what makes the X3 special. Not just the speed, not just the records, but the fact that it proved a crazy-looking idea was actually worth believing in. And honestly, that's how a lot of breakthroughs begin. So why did the world's fastest helicopter look so weird? Because every wing, every propeller, and every unusual design choice existed to solve a problem that engineers had been fighting for decades. What looked strange from the outside was actually a breakthrough hiding in plain sight. And maybe that's the lesson here. The ideas that change the future often look weird at first. If you enjoyed this story, make sure to subscribe for more incredible aviation innovations. There's always another machine pushing the impossible just a little further.